about inverse functions. So what is an inverse function? Well, normally in functions, we have our domain, which we put into the function, goes to range, which is the output of our function. But with an inverse function, it actually reverses this process where we start with the range and we go back to the domain. Now, this looks a bit funky, so let's clarify it with some examples. Let's say we have a function, and that function is f of x. And we'll denote its inverse to be g of x. So if we had, say, f of 1 equals 3, notice 1, that's my domain, my input into the function, and 3 is my range, the output. Now, using this example up here, this means that g of 3 should equal 1, because notice it's going to go backward from the range to the domain. We're going from 3 to the 1. G of 3 is 1. So if we had f of 2 was 4, then g of 4 would equal 2. And in general, if we have f of a equals b, then g of b equals a if and only if g of x is the inverse of f of x. So that's pretty cool, but let's talk about some notation for inverse functions. So if we write all of our inverse functions as g of x, or maybe we denote it with h of x, or some letter of x, it might be confused with our other functions that we might write down. And then we'll get them mixed up. It's a bit hard to clarify, so it's not the best method. So it's an easier method of writing inverse functions. Well, if we start with our base function f of x, then we denote the inverse of f of x to be f of negative 1 of x. So f of negative 1 of x is the inverse of f of x. Now that we know how to write it, let's talk about the formal definition of an inverse function. So two functions, f of x and g of x, are inverses if and only if f of g of x equals x and g of f of x equals x. And if both these are true, then g of x is the inverse of f of x. So let's break down these two statements right here. They look a bit funky, so let's think about what they're saying. Here, the first statement, it says f of g of x equals x. In other words, if f of g of x is x, then whatever value is coming out of g of x, when you put that into f of x, we should get back x. So it's just like what we were going over before. G of x equals some value of a, then f of x should reverse that process and have f of a equal x. And then we just replace g of x with a, and we have f of g of x equals x. And then it works in this other direction. So we should have g of f of x is x. If f of x is a, then if g of x is the inverse of f of x, then g of a should equal x, which means that g of f of x equals x. Now you might be wondering, we said that g of x was the inverse of f of x, not that f of x was the inverse of g of x. So why are both of these statements true? Well, if we break it down a bit, let's go to a new page. Let's say that we have our inverse functions. One is going from domain to range, and then the inverse goes from range to domain. But now if we view it from the perspective of the inverse function, we're having range to domain. The other function is actually reversing this process by going from domain to range. So essentially they're reversing each other. So when we go this way, domain to range, range to domain. We're reversing domain to range. But when we go back up, we're reversing range to domain. And we go domain to range. So essentially, they're inverses of each other. Not just g of x is the inverse of f of x. They're actually inverses of each other. So now when we go back here, it makes a little bit more sense of why both these statements are going to be true. Now, it's all cool knowing these funky statements, but can we actually use them? Well, let's try out a problem. Let's say that we had f of x equals 3x plus 5. And we want to know what f of negative 1 of x is equal to. Now, if we use the statement from earlier, we put g of x into f of x, notice that f of g of x is always equal to x. But notice that f of x is 3x plus 5. So therefore, f of g of x is 3g of x plus 5. And that's equal to x. And then we can solve for g of x to find that g of x is x minus 5 over 3. So using this wacky formula here, we could actually find the inverse of f of x, which was g of x, which was x minus 5 over 3. And we can try out some values to make sure it works. We put 1 into f of x. F of 1, that's going to be 8. We put 8 into g of x. G of 8, that's going to be 1. And we can do this with any value to make sure that it works. So f and g of x are inverses of each other. Now some functions don't actually have inverses. So what does that mean? Well, say we take the function f of x equals x squared. Now what is the inverse of f of x? We'll notice that both f of negative 1 and f of 1 both equal 1. So if I had some function f of negative 1 of x, and I plugged 1 into this inverse function, well now it has to be equal to both negative 1 and 1. But using the definition of a function can only have one output. So therefore, it cannot have two outputs like this, which means f of x squared does not have an inverse. But sometimes it actually can. Now what does that mean? We just proved that it couldn't have an inverse, so how can it have an inverse? Well, what if we went and we restricted the domain of f of x? If we let f of x, instead of having a domain of all real numbers, we restrict its domain to all non-negative numbers. or from 0 to infinity. Then there's only one input for each output of x. So if we have that sum f of x is equal to 1, we can only find one value of x that satisfies this. And this is true for any value over here. We could have 1, we could have 3, we could have 100, or any value. Because notice, x squared gets its repeats in negative numbers. So like, if we have some value of f of x is 3, then the values that would satisfy that would be the square root of 3, positive, or negative. And notice this negative sign here. It's getting its values from the negative side of x squared. So if we restrict the domain to get rid of the negative numbers, then we'll have a function with an inverse. Now, that's just one function. What about all the functions? How do we tell if a function has an inverse? We don't want to go through the long, tedious process of finding a function with an inverse, only to find out that it doesn't have an inverse. Well, that's where the horizontal line test comes in. Now, if we graph a function on the xy plane, let's take a graph of a function. And say the function looks like this. This is the graph of f of x. Now, if we can draw a horizontal line such that it hits the graph more than once, then the function does not have an inverse. Notice we can draw a horizontal line right here. So this function doesn't have an inverse because it intersects right here and right there. And we can even extend it to go over here. So why does this test work? What does this horizontal line tell us about the function? Well, notice this horizontal line, its x value is constant, or its y value is constant. So y is always going to be equal to some constant c for this horizontal line, which means each of these x values are different x values that would go into c. So say this was x is negative 1, x is positive 1, x is 3, for example, then all of these values would satisfy x where y is c. But notice when we go back to our original definition of having an inverse, if we had more than one value, such that f of x was equal to some constant c, then it couldn't have an inverse because then the inverse would have to be equal to all of those values, but a function cannot be equal to multiple values for the same value of x. Now, here are some examples of functions that do not have inverse that you'll likely come across. The biggest example are functions that are polynomials that have an even power, such that x squared, x to the 4th, x to the 6th, etc. But this is only with degree. If we have x cubed plus x squared, notice the degree of this polynomial is 3, which is an odd power. So we don't really care about the x squared, we only care about the highest power of x. So x cubed plus x squared would have an inverse, but x squared alone would not. And if we take a graph of these functions, it makes sense why. Here's the general graph of an even-powered function. Looks something like this. And as the power increases, say we had x to the power of 10, it gets really steep. Now then, if we take a graph of an odd-powered function such as x cubed, graph looks more like this. And notice we can't draw a horizontal line anywhere such that it hits the function twice. Now, why is this? Well, if we look at an odd power function, let's say x cubed. Now, if x cubed is equal to some value c, well, if c is positive, then there's only one positive number. That's not going to work. Because if we plug a negative number into x cubed, we get a negative number. If we plug a positive number into x cubed, we get a positive number. So regardless of what value we plug into x cubed, we always get one value in the end. Now let's talk about one more case of inverse functions where it can get slightly tricky. Let's say we had f of x equals the square root of x. What is the inverse of this function? Well, let's use our example. We've got f g of x is always equal to x. F of x square root of x, we have the square root of g of x equals x. We square both sides, we get g of x equals x squared. So x squared is our inverse. Hold on though. We just said that x squared doesn't have an inverse, so how can x squared be the inverse of f of x? Well, let's look back at our work to see what went wrong. The problem is right there. We have the square root of g of x equals x. Notice, though, if x is negative, this equation doesn't work. Because the square root of any number n is always greater than or equal to 0. So x is also greater than or equal to 0. And notice this is definitely true for f of x, because it has a domain of x is greater than or equal to 0. So the domain of g of x must also be x is greater than or equal to 0. And notice that when we restrict x on this domain, then g of x does in fact have an inverse, and then f of x and g of x, which we'll conveniently call f of negative 1 of x, are inverses of each other. So when dealing with square roots, it can be a little bit tricky, but remember, when you square each side of an equation, make sure to look at each side to make sure you're not squaring any negative numbers. Otherwise, you'll get funky